Hi. What we want to discuss today is something called differentiability at a point. So, what does it mean for a function to be differentiable at a point? That means that in plain terms the derivative exists, but more formally these two expressions here that we have, they are going to be equal. So what these expressions are, these are difference quotients with limits as x approaches c from the left and from the right. This is what we call one-sided derivatives. So if these two expressions are going to be equal, then the derivative will exist and the function will be differentiable at a point. So let's see how this works. With this example, so determine if this function is differentiable at 1. We are going to set up these two expressions. So x approaches 1 from the left. Let's start with that. Of f of x, which is going to be x squared minus 3x, minus f of 1, which is going to be negative 2, divided by x minus 1. It's going to give us x squared minus 3x plus 2 divided by x minus 1. Right? We can factor the numerator. This is actually 0 divided by 0. You usually don't have to worry about that. That's how it's going to be, because that's what the difference quotient is. So it's x minus 1 times x minus 2 divided by x minus 1. X minus 1's cancel, and now we can substitute 1 in here, and that's going to give us 1 minus 2, which is going to give us negative 1. So for the left, we got negative 1. Let's see what we're going to get on the when we do it from the right. So the limit as x approaches 1 from the right is x squared minus 3x minus negative 2 over x minus 1 equals the limit as x approaches 1 from the right, x squared minus 3x plus 2 over x minus 1. And you should see it's exactly the same expression, even though we're approaching from the left in one case, from the right in the other case. Direct substitution works here. We get negative 1. So since they're both equal, we can conclude that f of x is differentiable at x equals 1. Okay? What does it look like on the graph? So if you graph this function, this is what it looks like, and remember that one of the representations of the derivative at a point is the slope of the tangent line. As you can see, you have very nice and smooth curve, and there is a tangent line at that point. That's exactly what we got. So let's see how it works with another function. So we have the absolute value of x minus 2, and we want to see if it's differentiable at x equals 2. So the limit as x approaches 2 from the left is of x minus 2 minus 0 divided by x minus 2. So it's the absolute value of x minus 2 divided by x minus 2. So this is not as easy as the other problem, because you can't do these algebraic transformations here. But let's think about this together. What do we know here? It's essentially the same expression. As the numerator is always going to be positive or 0, right? But in this case it's actually 0. But the denominator, as we approach 2, remember we are talking about being very close to 2 from the left. So when we are going to be very close to 2 from the left, while the numerator is positive, the denominator, when you take a slightly smaller number, slightly smaller than 2, the denominator is going to be negative. So it's actually positive divided by negative, right? It's the same expression. Just think about this. If it was 5 divided by negative 5, for example, or 3 divided by negative 3, you are going to get negative 1. So on the left it's negative 1. Let's see what's going to happen on the right. So we already know it's going to be the same expression. I'm just going to copy that. So how is this going to be different? While the numerator is still going to be positive, the denominator is going to be positive as well. So this is positive over positive, right? Same expression, same value. Basically what we're saying is, as long as we're staying on the right side of 2, we are going to be getting the same exact number on top and the bottom, and they're both going to be positive. And here the answer is 1. So we got different values. So this function is not differentiable. So g of x is not differentiable at x equals 2. Now you should recognize this function. This is an absolute value function. And what happens here is, if you are actually going to do it, you will see the following. You will see that this function looks like this. And what we have here is, at 2, we have the vertex of this function, and there is a sharp turn. So what can we assume so far from things that we saw? The function needs to be continuous at the point, and if it looks like the function is smooth, because the first example the graph was smooth, this one is not at 2. The function should be differentiable. So the first assumption about the continuity is correct, and we're going to discuss this in a moment. What about the second assumption? Does every function that's going to be smooth at a particular point, near a particular point, is going to be differentiable there? Well, almost always, but not all the time. Here is a classical example. So if you're going to do this with the function x to the power 1/3, which is basically a cube root of x, you want to see if it's differentiable at 0. Let's see the limit as x approaches 0 from the left of x to the power 1/3 minus 0 divided by x minus 0, which is going to give us the limit as x approaches 0 from the left, and that's going to give us, so it's x to the power 1/3 divided by x. It's actually going to give us 1 over x to the power 2/3, or x to the power negative 2/3 if you want to write it like this. So the problem is, well, actually let me write that as a fraction without the negative exponent. Here's the problem. This one is infinity. Okay? And if you do the same thing from the right, you are basically going to get infinity as well. It's the same exact workout, and we're going to get infinity. So infinity is not a number. Remember, to have a limit, we need to have finite values. You don't have a finite value, the function is not differentiable. So h of x is not differentiable at x equals 0. So the graph of this function looks like this, and what happens is at 0 you are actually going to have a tangent line that is vertical, and vertical line has undefined slope. So even though this function is continuous everywhere and it is smooth everywhere, this function is not going to be differentiable at that point because you have a vertical tangent line, if you think in terms of that. So some important stuff. So the function, first of all, needs to be continuous everywhere, and the graph is, we're talking about h of x, so the function is continuous everywhere, the graph is smooth, the tangent line is vertical, it's 0, so that's why it's undefined. But, so first of all, in order to even consider a function for differentiability, it must be continuous. We talked about this earlier. The function must be continuous to even get into the discussion of differentiability. So continuity is what they call a necessary condition for differentiability. Differentiability in turn is going to automatically imply continuity. That means if the function is continuous, is differentiable, my apologies, it should say differentiable. If the function is differentiable, it will be continuous. Okay, so differentiability is going to be sufficient condition for continuity. So So here's what we're gonna conclude so far. If the function is differentiable at c, it will be automatically continuous at c. If the function is not continuous at c, there is no way the function can be differentiable at c. And if the function is continuous at c, then the function may or may not be differential, but then you're going to need further analysis. Okay? But we know that differentiability will imply continuity. Alright? So, these problems are often used with piecewise function, because with piecewise functions you don't know what's going on, as you already know. Sometimes things get interesting on the different sides. So we want to see if this particular function is differentiable at x equals 1. Each one of these functions individually is actually differentiable everywhere if you ignore these. Okay, it's a linear function, a quadratic function, they're both continuous and smooth. So the question is, what happens at 1? So the first thing we need to do is see if the function is continuous at 1. So for that we're going to need to do the limit as x approaches 1 from the left of f of x, which is basically, this is where it's less than 1, so this is the left side, which is going to be the limit as x approaches 1 from the left of 2x plus 1, which is going to give us 3. Right? And then we also have to do the right hand side. So the limit as x approaches 1 from the right of f of x. That's the right side here. So we're going to do the limit as x approaches 1 from the right of x squared plus 1, and we substitute 1, x squared plus 2, and that's going to give us 3 as well. So the function is continuous. Because you do need to establish this first. So what about differentiability now? Because now we know it's continuous, we can go ahead and analyze differentiability. So the limit as x approaches 1 from the left of the difference quotient. So when we are on the left side, this is our function, the first one, right? This is going to be f of x minus f of 1 divided by x minus 1. So this is going to be the limit as x approaches 1 from the left. The numerator will be 2x plus 1 minus 3 divided by x minus 1. So if we continue with this, we're going to get the limit as x approaches 1 from the left of 2x minus 2 divided by x minus 1. So here if we factor out 2, we're getting 2. So the left hand derivative is going to be 2. What about the one on the right side? The limit as x approaches 1 from the right. So same expression here, but the function is going to be different because the left side is the second function. It is going to be x squared plus 2 minus 3. X squared plus 2, correct, minus 3 over x minus 1. So this is going to be the limit as x approaches 1 from the right of x squared minus 1 divided by x minus 1. Correct? So we can see here that this the numerator is factorable. So it's x minus 1 times x plus 1 over x minus 1. These things cancel. Direct substitution gives you 2. We have the same exact value, so the function is differentiable. So we can say that f of x is differentiable at x equals 1. Okay? Moving on. this function here. So again, we need to check continuity first. So the limit as x approaches 2 from the left of g of x. The left side of 2 is the first expression. It's going to be the limit as x approaches 2 from the left of negative x squared plus 3x. Right, so we are going to take 2, substitute that, so it's going to be negative 2 squared, so it's negative 4 plus 3 times 2 is 6, and that's 2. Right. So continuing with this analysis, see if it's continuous. So now it's going to be the second function, the limit as x approaches 2 from the right of negative 1/2 x plus 3. Direct substitution here will give us negative 1 plus 3, which is also 2, so it's continuous. Right? So now we can analyze the differentiability. So we're going to have the limit as x approaches 2 from the left of g of x minus g of 2 over x minus 2. Alright, that's the limit as x approaches 2 from the left. So on the left is the first function, so it's going to be negative x squared plus 3x, and then we know that g of 2 is actually 2, so plus 2. My bad, it's minus 2 over x minus 2. I can take care of this negative sign. If I factor out the negative sign, I can actually, this is negative x squared minus 3x plus 2. And this can be factored as x minus 1 times x minus 2 divided by x minus 2. So x minus 2 cancels. Using the direct substitution here, we are going to get negative 1. Okay. So the limit as x approaches 2 from the right of g of x minus g of 2 over x minus 2. So what are we getting here? We're going to get the limit. This is the second equation we're going to be using now because we're on the left of 2, I'm sorry, on the right of 2. So it's going to be negative 1/2 x plus 3 minus 2 divided by x minus 2. So it is going to be the limit as x approaches 2 from the right of negative 1/2 x plus 1 divided by x minus 2. So what we're going to do is we're going to multiply the top and the bottom by 2. It's one of the possible ways to handle that, to get rid of that fraction. It's just some simple algebraic work. I should say arithmetic work. Okay, so what are we getting here? The limit as x approaches 2 from the right. The numerator is going to give us negative x plus 2 divided by x minus 2. And these are opposites of each other, and the answer here is going to be negative 1 as well. So it is differentiable. At x equals 2. Okay. Let's take a look at the next example. So this is what I need to warn you about here. Sometimes when students do these types of problems, they are too quick to ignore the continuity and they just jump into the differentiability part. And what's going to happen here, if you do this, you will actually find that the derivative of the left-hand derivative and the right-hand derivative of this function will be the same. But this function is not continuous. So the limit as x approaches 1 from the left of h of x, we're using the first equation, so it's the limit as x approaches 1 from the left of 2x squared minus 8x. So when we substitute 1 into this expression, we are going to get 2 minus 8, which is negative 6. And then when we do the limit of this function as x approaches 1 from the right, we use the second function, so it's the limit as x approaches 1 from the right of negative 4x plus 2, and it's going to give us negative 2. These two values are not the same. It's not continuous. Okay, that means what? That means you do not continue with any further analysis, because if the function is not continuous, there is no way it's going to be differentiable at that point. Okay. And this is a fairly typical example. We want to find values of a and b so that f of x is differentiable at x equals negative 1. So what we have here is a line. The first equation is a linear equation, the second one is a parabola, so we want them basically in plane terms. We want them to join together, and we also want them to have a smooth transition from one to the other. So the first thing that we do is, if you set it up as this, so as x approaches negative 1, as x approaches negative 1 from the left of f of x, that's going to be the limit of the first expression, x approaches negative 1 from the left of ax plus b. So even though we don't know what a and b are, we can substitute negative 1 in here, there is no issue here, and you're going to get negative a plus b, right? And then the limit as x approaches negative 1 from the right of f of x is going to be the limit as x approaches negative 1 from the right of the second expression, which is x squared minus 2x. And we substitute negative 1 here, so negative 1 squared is 1, minus 2 times negative 1, so it's plus 2, and it's going to give you 3. So we want those two things equal, right, because we want the function to be continuous. So we know that negative a plus b has to equal 3. Okay, but obviously we're not going to have a unique solution here, so now this was the continuity part. Because we need to make sure the function is continuous and differentiable. So the differentiability part is going to be the limit as x approaches negative 1 from the left. It's going to be f of x, so it's f of x minus, so plus 1 over, no, it's going to be minus, I'm sorry, minus the value of the function at negative 1 divided by x plus 1. So what we get here is f of, so it's a x plus b minus, so plus a minus b, so b's cancel, over x plus 1. It's going to be the limit as x approaches negative 1 from the left of, we got ax plus a, we can factor out a, x plus 1 divided by x plus 1. It's going to equal a. So the slope on this side is going to be a, which is consistent with the slope of the line itself, right? And then we're going to have for the right hand side, x approaches negative 1 from the right, is going to be f of x minus 3, which is what the value of this expression is going to be when you substitute negative 1 over x plus 1. So in this case, f of x is going to be the second expression, right? So we're going to have the limit as x approaches -1 from the right. This is going to be x squared minus 2x minus 3 divided by x plus 1. So it's going to be the limit as x approaches -1 from the right. This can be factored. It's x minus 3 times x plus 1 divided by x plus 1. X plus 1 cancels. You substitute -1 here. It gives you -4. So we want these two limits here, the one-sided derivatives, to be equal. So right there we can say that a is going to equal -4, right? Because these two values here will need to be equal, right? And now that we know a, we can go ahead and go back to this expression here and substitute this value to find the value of b. So -4 plus b equals 3, and then from there we can see that b is going to equal -1. Okay, and that's how you do problems like this. They're very common if you're taking AP calculus. The problems like this are very common in the AP exam. Okay, I hope this helps.